Welcome back to the deep dive. Ever felt, completely lost trying to figure out how some huge complex system actually works, like airline reservations or maybe one of those giant automated warehouses?
Absolutely. It can feel like staring at a tangled mess of wires.
Exactly. Well, this deep dive should help bring some clarity. Today, we're unpacking a really fundamental tool in system analysis and design, data flow diagrams,
Mm,
DFDs for short.
right.
So what is a DFD, essentially? Well, it's basically a visual model. Think of it like the highest level map of a system.
Yeah, it graphically shows how data moves. Where it starts, how it gets changed or transformed, and where it ends up.
It's kind of the common language, isn't it?
Mm.
Allows developers, analysts, business folks to all get on the same page about what the system does without needing to look at any code.
That's a great way to put it. And what's really fascinating here, I think, is that DFDs aren't just, well, pretty pictures. They're almost like the foundation of the system's design contract.
A contract. Interesting.
Yeah, because drawing the map correctly, that's only half the job. If you have a poorly structured map or one that's inconsistent, that leads straight to misunderstandings, big system errors, and frankly, a lot of wasted time and money.
Okay, so getting it right is crucial.
Absolutely. So our mission today is really to dive into the two pillars that make a DFD reliable, useful, and scalable. First, there's decomposition.
Okay.
That's the art of breaking a huge system down, like taking a skyscraper view and getting down to the individual bricks.
Makes sense. And the second?
And second, balancing. This one's non-negotiable. It's about keeping absolute consistency as you do that breaking down. You really need to grasp these two concepts to ensure the system hangs together properly and, you don't just overload people with information.
Got it. Decomposition and balancing. Let's dig in. All right. Like any map, we need a legend, right? Vocabulary. Before we start tracing those complex data flows, let's quickly nail down the four core components you'll find on, well, pretty much every DFD.
Good idea. The building blocks.
First up, you've got the engines of the system. Processes. These are the activities that actually do something to the data. They transform inputs into outputs.
Yeah.
Represents the business logic.
Okay.
And the key rule here, which I think is more about insight than just definition, is that processes have to be labeled with an active verb-noun combo, like process order or verify credentials.
Yeah. And why is that active verb rule so important?
Good question. You tell us.
Well, it forces the analyst to really think about the transformation. If you label a process something passive, like, say, order handling, well, what does that actually mean?
Right. Could be anything.
It could be hiding multiple steps, or you might be missing the actual business logic completely.
Yeah.
Using verb noun kind of forces clarity. It makes sure every process box is actually performing a defined transformation.
Okay, active verbs. Got it. What's next?
Next, you have the highways, as you called them, data flows.
Right, the arrows.
Yep. Simple arrows showing the movement of information. They always get labeled with a noun like customer ID or validated payment. Shows direction. Sometimes they might go both ways, bidirectional, but honestly, usually you keep them one way just to keep things clearer.
Okay. Processes transform, data flows move. Where does the data rest?
That brings us to the data stores. Think of these like parking lots for data, a repository where data sits when it's not actively being processed.
Like a database table or a file.
Could be, yeah. They're labeled as nouns too, like customer data or maybe product catalog. And the flow direction matters here. An arrow to a store means you're writing or updating data. An arrow from the store means you're reading or retrieving it.
Makes sense. Data has to be managed. It doesn't just appear.
Exactly. It has to come from somewhere and go somewhere via a process.
Okay, one more component. The boundary keepers.
Right, external entities. Sometimes people call them terminators. These represent the sources or destinations of data that are outside the system you're actually modeling.
Like a customer. Or maybe the tax authority. Or even another system, like a payment gateway.
Precisely. Could be any of those. And here's a really, really critical rule about boundaries.
Okay.
External entities must interact only with processes. Data can't just magically flow from, say, a customer straight into a data store without a process sitting in the middle.
Why not? Seems like it could happen.
Well, think about it. That process in the middle, that is your system's control point. It's where you validate the input, apply business rules, maybe transform the data format. Without that process, how would you test the system? How would you ensure data integrity? How would you even know what part of your system is responsible for handling that interaction?
Okay. So the rule isn't arbitrary. It's about defining control and testability.
Exactly. That rule makes the whole thing manageable and, well, testable.
Okay, that rule about boundaries and processes makes a lot of sense, but it brings up a big question for me. How do you possibly apply all these rules, processes, flows, stores, entities when you're dealing with a really complex system?
Yeah.
Something with maybe hundreds or even thousands of steps.
Yeah, that's the challenge, isn't it? If you tried to draw it all on one diagram.
It'd be a nightmare. Just spaghetti everywhere.
Mhm.
Unreadable.
Totally unreadable.
Yeah.
And that's precisely where decomposition comes to the rescue. It's really the foundation for turning some huge, confusing project into chunks you can actually understand and manage.
So breaking it down.
Exactly. It's a systematic process. You progressively take a high-level process and detail it out into smaller, more granular sub-processes. Why? Well, simply to make the whole thing less complex to look at, reduce the cognitive load on whoever's trying to understand it, and also to help spot problems, bottlenecks, redundancies that might be hidden inside those bigger process blocks.
I like the analogy you used before, like a city map. Start wide, then zoom in.
Right. You start with the whole city, then maybe zoom into a neighborhood, then a specific block, then maybe the floor plan of a building on that block. Decomposition is the same idea for systems.
And it's not just random zooming, is it? There's a structure, a hierarchy with numbering.
Absolutely structured. At the very, very top, the highest level of abstraction, you have the context diagram.
Okay, context diagram. Let's be super clear for everyone listening. This is the entire system shown as just one single process box.
Right.
Right, usually labeled process 0.
Yep, that's it, process 0. It shows the system's absolute boundary, who the external entities are that interact with it, and only the major data flows coming in and going out. It tells you what the system does overall, but completely hides the how.
Gotcha. The 30,000-foot view, level 0 abstraction.
Precisely. Then the next step is you take that single box, process 0, and you essentially explode it. You open it up to reveal the level 0 DFD. Note the slight naming difference there. Context diagram shows process 0, level 0 DFD explodes process 0.
Okay. Context versus level 0 DFD. Subtle, but important.
Yes. And this level 0 DFD shows the system's main primary functions. The processes here get whole numbers, like 1.0 handle orders, 2.0 manage inventory, 3.0 generate reports, something like that. And this is the first level where you typically start showing internal data stores.
Okay, so we've broken down the main system into its biggest parts. What then?
You keep going. Once you've defined those primary functions, you continue the descent. Let's say we take process 1.0, handle orders. If we need more detail on how that works, we break it down further to create the level 1 DFD for process 1.0.
In the numbering follows.
Exactly. This level 1 DFD decomposes 1.0 into its sub-processes using decimal notation. So you'd see maybe 1.1 receive order, 1.2 process payment, 1.3 dispatch notification.
That numbering, like 1.1, 1.2, seems really important.
Oh, it's crucial. It provides structural accountability. You immediately know which parent process any sub-process belongs to. Think about a big project. This tells you who owns that piece of functionality, which team needs to build it, or which business unit defines the rules for that specific step.
So it's traceability built in.
Exactly. And this decomposition, this iterative detailing, can continue down to level N, DFDs, 1.1.1, 1.1.2, and so on. You keep going until every process is functionally simple, clear, and unambiguous enough that someone could actually implement it directly without needing further breakdown.
Okay, that leads to the million-dollar question, doesn't it? When do you stop drilling down? How do you know you haven't gone too far?
That's a great question, and there's a practical rule of thumb. The standard advice is stop when the process is simple and manageable. What does that mean? Usually it means you could describe everything that process does in, say, a single page of specifications.
Okay.
If you keep decomposing beyond that point, you run the risk of over-decomposition. And instead of adding clarity, you actually just create a different kind of complexity. Too many tiny boxes, too many diagrams. It defeats the purpose.
All right, so decomposition is how we manage the sheer scale, the complexity. But then there's the integrity piece, right? Once you start breaking down process 0 into 1.0, 2.0, 3.0, and then you break 1.0 down into 1.1, 1.2, 1.3, how on earth do you make absolutely sure you haven't accidentally invented new data flows that shouldn't be there?
Or worse.
Or worse, yeah.
Yeah.
Lost track of some critical piece of data that the higher levels showed was essential.
Bingo. That's where balancing comes in. It is the consistency rule. It's what keeps your entire decomposed hierarchy trustworthy and accurate.
Okay, so define balancing for us. What does it mean precisely?
It's actually quite simple in concept, though sometimes tricky in practice. Balancing means that all the data flows that enter or exit a higher level process, the parent process, must perfectly match the total sum of data flows entering or exiting the lower level decomposed DFD, the child diagram, for that specific process.
Okay, like inputs and outputs have to match across levels.
Exactly. Think of it as a closed system contract between the parent diagram and the child diagram. Nothing can be created or destroyed as you zoom in or out, only elaborated upon inside the boundary.
And this isn't just about making the diagrams look neat, is it? There are real consequences if you don't balance.
Oh, absolutely catastrophic consequences, potentially. Poor balancing breaks that data contract we mentioned. It leads directly to misinterpreting requirements. It can mean processes are missing the inputs they critically need to function, or it can cause data inconsistencies that ripple through and destabilize the entire system design.
Wow. So like if your level 0 diagram shows you need a customer ID to kick off the whole order process,
Right.
but then the level 1 diagram that breaks down order process somehow forgets to show the customer ID coming in.
Then your system is fundamentally broken on paper before a single line of code gets written. The downstream processes that need that customer ID won't get it. Balancing prevents exactly that kind of error.
Okay, let's make this really concrete. You mentioned a library system example earlier. Can we walk through balancing with that?
Yeah, perfect example. Let's track the data carefully. Imagine your level 0 DFD has that process we talked about. Maybe it's 2.0 borrow book.
Okay, process 2.0, borrow book.
And it interacts with an external entity, the member. The key external flows shown at this level 0 are, let's say, book request coming in from the member and book issuance confirmation going out to the member.
All right, that's the parent view. Two external flows crossing the boundary of process 2.0.
Exactly. Now, we decide we need more detail, so we decompose or explode process 2.0 into its level 1 DFD. This child diagram shows the internal steps, maybe 2.1, verify membership, 2.2, check book availability, and 2.3, issue book.
Okay, those are the sub-processes inside 2.0.
Right. And inside this level 1 diagram, you'll likely see new internal data flows. For instance, process 2.1 might need to read from an internal data store called membership records, and 2.2 probably needs to check the inventory data store.
So we see new flows connecting to data stores appear at this lower level.
Yeah.
That's allowed.
Absolutely. That's showing the internal detail. And this is the crucial part for balancing, what about those original external flows? Book request and book issuance confirmation.
Yeah, what happens to them?
The rule of balancing dictates they must still cross the boundary of this level 1 diagram exactly as they cross the boundary of the parent process 2.0. So the book request flow must be shown entering the level 1 diagram somewhere, maybe that goes into process 2.1, and the book issuance confirmation must be shown exiting the level 1 diagram. Perhaps it comes out of process 2.3.
Ah, I see. So the interaction with the outside world, represented by those external flows, has to be preserved perfectly between levels.
Perfectly. You can add all sorts of internal complexity, new flows between sub-processes, flows to and from data stores like membership status or book availability result. But the data crossing the boundary defined by the parent process must remain identical in the child diagram. If that level 1 diagram for borrow book doesn't show book requests coming in or doesn't show book issuance confirmation going out, you have an unbalanced diagram. You've broken the hierarchy. You've essentially lost or gained data at the boundary.
That's a brilliant illustration. It's about preserving that external conversation. So key techniques here must involve things like really consistent naming for flows across levels.
Absolutely critical. Consistent naming for data flows, and also consistent naming and representation of data stores if they're accessed by processes shown on different levels. It stops you thinking you've lost a flow when maybe you just accidentally renamed it slightly between diagrams.
Okay, we've got the structure down with decomposition and the integrity locked in with balancing. Now let's shift perspective a bit, because DFDs aren't always used for the exact same purpose, are they? There are different types.
That's right. They aren't a one-size-fits-all tool. Generally, we talk about two main flavors, reflecting different goals or, well, different viewpoints.
Which are?
First, you have logical DFDs. These focus purely on what the business processes are. How does data flow conceptually to support the business? Think of it like the architect's initial blueprint. It shows you need a kitchen, and generally what the kitchen needs to do, store food, allow for cooking. It ignores the specific appliances or counter materials for now.
This is the business perspective, usually done by a business analyst, maybe.
Exactly. It's about understanding and documenting the business requirements and rules. Then you have physical DFDs.
And these are more
much more concrete. They focus on how that data flow is actually implemented in the real world. This is more like the builder's detailed plan. It specifies which database table holds the customer data, which software application runs the process payment step, maybe even which specific web form collects the book request.
So the system perspective may be created by a developer or a database analyst.
Typically, yes. It shifts from the abstract what of the logical DFD to the concrete how of the physical DFD. But crucially, the underlying flow structure and the rules of decomposition and balancing still apply. You still need to balance a physical DFD against its corresponding logical process.
Interesting. So regardless of whether it's logical or physical, or which level of decomposition we're looking at, there's some hard and fast rules that DFDs just have to follow to be valid.
Absolutely. Non-negotiable rules to maintain their usefulness and integrity.
Okay, let's recap those. We touched on one earlier. Data cannot flow directly between two external entities. Why is that one so strict again? Seems like two external systems might talk to each other.
They might, but if they do, that interaction is, by definition, outside the scope of the system you are modeling with this DFD. If System A talks directly to System B, and your DFD is only modeling System A, then System B is just an external entity. If you need to manage or mediate the conversation between A and B, you have to put a process inside your system boundary to handle that. The rule forces you to be explicit about what's inside versus outside your control.
Okay, that clarifies it, defines the system boundary.
Yeah.
So that's rule one. What else?
Rule 2, data cannot flow directly between two data stores. You can't just magically copy data from the customer data store to the order history data store.
Use a process.
Always needs a process in between to read from one, possibly transform or validate, and then write to the other. Again, it's about control and defined logic.
Makes sense. Rule 3.
Data cannot flow directly between an external entity and a data store. We covered this again. You need a process to act as the gatekeeper, the validator, the transformer.
The intermediary.
And finally, a structural rule. Every single process must have at least one data flow going in and at least one data flow coming out.
Why's that?
Well, think about it. A process with only inputs and no outputs, that's a black hole. Data goes in and disappears. Doesn't make sense. A process with only outputs and no inputs, that's a miracle. Data magically appears from nowhere. Both indicate something's wrong, probably missing logic, or a mistake in the diagram.
Black holes and miracles. Good way to remember it. So beyond these hard rules, any best practices for just keeping diagrams clear and useful?
Definitely. Keep it simple. Stick to that stop decomposing when a process is simple rule. Don't overdo it. Standardize your naming conventions rigorously for processes, flows, and stores. And maybe most importantly, validate, validate, validate. Show the diagrams to the actual users, the stakeholders, the business experts. Make sure the DFD accurately reflects the real-world system they know. #tag atra contra.
Okay, this has been incredibly clarifying. We've really unpacked DFDs, not just as pictures, but as this essential visual contract for system design. We covered the structure through decomposition for handling scale.
Right? Breaking it down.
And the critical importance of balancing for maintaining that consistency and data integrity across all the different levels of detail. Hopefully you listening now feel equipped not just to read a DFD, but maybe even critique its structural soundness.
Yeah, and system analysis really does hinge on that kind of clarity. But, we did note that DFDs deliberately leave certain things out. They show what data flows, but they don't explicitly show things like security protocols or performance requirements or specific UI designs.
Non-functional requirements.
Exactly. So here's something to think about, a provocative thought maybe. Considering that limitation, how does a system analyst ensure that those critical non-functional requirements, things like, say, mandatory encryption on a data flow, or the need for a process to respond within 500 milliseconds, or complex access controls, how are those requirements consistently mapped and, in a sense, balanced across the system's hierarchy, even though the DFD itself doesn't explicitly draw them?
That's a great question. It implies there's another layer of architectural thinking that needs to parallel the DFD structure.
Precisely. It often requires different models or documentation, supplementary views that need their own form of consistency checking alongside the data flow, figuring out how those different views mesh without conflict. That's a challenge every good analyst wrestles with.
A fantastic thought to leave us with the map. Shows the roads, but not necessarily the speed limits or the toll booths. Thank you so much for diving deep into the structural integrity of system design with us today.
My pleasure.
And we really encourage you, our listeners, to maybe try applying these ideas, decomposition, balancing, maintaining consistency to any complex problem you're facing, whether it's technical or not. It's a powerful way to think. We'll catch you on the next deep dive.